We learned in yesterday's lesson that when electric current passes through a wire, it generates an electric field around it, which we can call magnetic field of a current. And the direction of that magnetic field with respect to current can be found using right-hand rule. And when that wire forms a loop, the electric field or magnetic field have the pattern that is shown in diagram. Now, I would like you to imagine a situation where you're putting this wire in another magnetic field. What will happen if the magnetic field of the current in the wire and the magnetic field of the magnet interact? Here we see a U-shaped magnet with north and south poles, and there is a wire that is passing between the poles. When you switch on the current, the wire moves out of the magnet, and when the current is switched off, it comes back to its original position. Basically, the magnetic field due to the electric current in the wire interacts with the magnetic field of the magnet, hence a force is applied, hence the wire is pushed out of the magnet. There are three quantities which we need to consider here. One is the direction of the current. Obviously, that is in this direction as indicated in the diagram. The magnetic field of the magnet goes from north to south pole, that we already know. The wire is pushed out of the magnet upwards, hence, there we go. So all of these forces are perpendicular to each other. As we saw earlier, when electric current is passing through a wire and that wire is put between the north and south pole of a magnet, a force is applied on the wire and that is pushed out of the magnet. Now we will try to find out how can we find the direction of the force or the magnetic field or the current if we know the other two. Before moving on to that, we must understand that magnetic field direction of the magnet is from north to south pole, and the current direction is from positive terminal to the negative terminal of the battery. Well, at least of the conventional current. In this diagram, a piece of that wire is shown between the north and south pole of the magnet. As we know that the direction of the magnetic field is from north to south pole, hence this arrow over here shows the direction from north to south pole. Then we need to understand, or we need to know, the direction of the current, and that is in this direction, which means current is entering at that end and leaving this end of the wire. Now, if we know these two, we can understand, or we can find out the direction of the force by using our left hand. Finding the direction of force or finding the direction of the current using left hand is called Fleming's left hand rule. And you need to make sure that your left hand, the first finger and the middle finger and the thumb, they're all perpendicular to each other. Okay, like this. If I can show you on the camera, this thumb and this finger, they are perpendicular. Hence, this finger and this finger, they are perpendicular to each other. So you need to make sure that they are super straight. Here we have the structure of a DC motor. In this example, we are going to see how the electric current passing through this coil affect it being between the north and south pole of the magnet and how it rotates. Let's switch on the circuit. As you can see, it is rotating between the poles of the magnet. It will not rotate if the magnet is removed. In this case, the direction of the current is shown with the red arrows. As you can see, this coil is going down now. As it is going down, and as it will come towards the other end or towards the other pole, the direction of the current will change. Here now, did you see that the direction of the current flipped? It got flipped because we want this coil to keep on rotating in one direction. If the direction of the current does not change, it will keep on moving at the same point, like this. And it will not be able to rotate completely. To enable the complete rotation of this coil, we are keeping a gap here. As you can see, there are gaps, hence the circuit is broken for a moment. And as the second terminal or the second edge of the coil touches, the direction of the current is reversed.